Now let us consider a system with spin inversion symmetry, not spin inversion, rather space inversion, system with inversion symmetry. So what does inversion do? Inversion operator for inversion J takes R to minus R and J takes P to minus P. So, and since the system has inversion symmetry, since the system has inversion symmetry, J psi is an eigenvalue, is an eigenfunction of H if psi is an eigenfunction. Simply because J and H commute, so that JH psi is equal to EJ psi and this is equal to HJ psi because they commute, therefore HJ psi is equal to E times J psi. Okay. Now let us see what happens to the band states when I operate by J on the block states. So the block state is psi k of R is equal to e to the I k dot R U k of R. So when I take J psi k of R, this gives me e to the minus I k dot R U k of minus R. Now let us see what is U k of minus R. So in order to see that, what we will do is the following, that is write down pseudo Schrodinger equation for U k of R. We have p squared by 2m plus h cross by m k dot p plus v of R U k of R is equal to E k U k of R. Now if I operate by the J on this pseudo Hamiltonian, then what happens is that J on that one will give me p squared by 2m plus h cross by m k dot p plus v of R U k of R will give me p squared by 2m minus h cross by m k dot p plus v of minus R times U k of minus R equal to E k U k of minus R. Now V of minus R is equal to V of R, and so what I can write down is the following, that is, and U k of minus R I can actually write as U minus k of R and what I will get is p squared by 2m minus h cross by m k dot p plus v of R u minus k of R is equal to E k u minus k of R. So this means that E k up is equal to E minus k up, and Ek down is equal to E of minus k down. Or in other words, when both inversion and time reversal symmetry exists, we have Ek up is equal to Ek down is equal to E minus k up equal to E minus k down. So, which means that I have the full symmetry in the band, and if I am looking at, say for example, the p bands, assume we have one electron in a p band. Then what happens is that the band structure will look like this. So, there are 3 branches because this is a p band, and all the branches will have this symmetry. Let me remove this. And at k equal to 0, all of them are degenerate. This is the energy. So, at k equal to 0, all the p bands are degenerate in a cubic crystal. I have taken a cubic crystal for convenience. Are degenerate as and each one of them will have either spin half or spin minus half, and all of them will be degenerate. Okay. So, now let me see what happens when I introduce the spin orbit interaction. I have just introduced, this is the case where I have both time reversal and inversion. Okay. Now, let me think of a spin orbit interaction. So, if I introduce a spin orbit interaction, since I am dealing with p bands have L is equal to 1 and electron has S equal to electron has S equal to half. So, the J states are, the J values allowed are J equal to 3 by 2 and J equal to half, and I will find in this case the spin orbit splitting breaks the bond and breaks the degeneracy there of the 6-fold degeneracy that I have at k equal to 0. So, at k equal to 0 without spin orbit interaction, the states are 6-fold degenerate. Px, Py, Pz and spin equal to Ms equal to plus minus half are all degenerate. Now, when I have spin orbit interaction, J equal to 3 by 2 and J equal to half will be split, and let me also assume that we have spin orbit interaction, we also have inversion symmetry. So then in that case the bands will look like this. K, and then I have a j equal to half state, and then I have j equal to 3/2 states. So I have this degeneracy of Ek plus j equal to 3/2 equal to Ek minus j equal to minus 3/2 and so forth. So basically I will have rather I will have 4 bands, sorry, one second. Oh, I said I have got inversion symmetry. So with inversion this is the band structure that I have. So if I do not have inversion, inversion symmetry, but we have spin orbit interaction. Then of course the j equal to plus minus mj equal to plus minus half and mj equal to plus minus 3/2 and plus minus half, they will split, and I will have the following. Let me pass it through the middle. This is k equal to 0, and this is the energy, and then I have the others will split into 4 bands. Okay, so you have 4-fold degeneracy and 2-fold degeneracy at k equal to 0, and at k not equal to 0 the bands are fully split. That means you have 6 bands corresponding to plus k mj equal to 3/2 minus k mj equal to 3/2 and then plus k mj equal to half minus k comma mj equal to minus half. These are for j equal to 3/2, and then for j equal to half you will have plus k mj equal to half and minus k, and so I'll have 6 bands. So I'll have k and mj equal to half. There is no plus and minus, I am sorry, because k is all possible values of k. And I also have k comma mj equal to minus half, because when you move away from 0, then obviously on which side of the vertical you know the value of k, whether it is positive or negative, and you have 4 bands corresponding to j equal to 3/2 and 2 bands corresponding to j equal to half, and each are distinguished by different values of mj. So this is how the energy band picture will look when you have spin orbit interaction. Well, let me look at spin orbit interaction a little more in detail. Okay. So what happens is that the spin orbit interaction term that we had interaction term is actually h spin orbit equal to sum over I or Si dot Li, and this is with psi Ri equal to h cross squared by 2 mc squared, into 1 upon Ri del V by del Ri. So, this we get this expression that we get, this is true when the electric when the potential V of R, when the potential is spherically symmetric. But supposing I am dealing with, say, a plane, a two-dimensional solid, the fields are not spherically symmetric. Because you have an asymmetry. So, supposing I am having a planar solid like this, then there is a field. If this is in the xy plane, then there is a field along the z direction, and this field is, let us say, let the electric field be E naught times z. So, if this is the case, then this electric field also causes a magnetic field. And the magnetic field is given by B equal to minus V cross E by C squared. So, and this magnetic field interacts with the spin. Notice that E is equal to E naught z. So, when this happens, I get another spin orbit interaction term. We get an additional spin orbit interaction term corresponding to this anisotropic or the directional field E z, and we get an additional spin orbit interaction term. And this is called the Rashba term. This will be minus alpha r sigma cross p dot z. So, alpha r is the Rashba Hamiltonian. This Hamiltonian occurs simply because we have a lack of inversion symmetry, and so there is an electric field inside the system. This can happen either in a two-dimensional system or a three-dimensional system without inversion symmetry. So, the alpha r is called the Rashba constant. And alpha r is actually given by minus g mu b, which is a Bohr magnetron. G is the gyromagnetic ratio, divided by 2 mc squared times E naught is the electric field. Okay. So, this is the Rashba constant. And what is interesting about this one, or I can again, let me write it h of r again in another fashion, which is minus alpha r times sigma x p y minus sigma y p x. Well, what is interesting about this is that the spin orbit interaction strength is controlled by the field strength E naught. So, supposing you were to apply an external field, so you can actually apply a very strong field or a very weak field, and thereby you can make sure the splitting between the different states or spin states are actually controlled by an electric field. And this is very important for spintronic applications, because in spintronics you want to adjust the gap between the two different spin states by varying the electric field, and that is possible with this one. Okay, now is a bit funny, that is, of course, the correct expression for alpha r, actually if you do a proper relativistic calculation, then alpha r has a correct form, which is minus g mu b h cross by 4 mc squared, not 2 mc squared, times E naught, and this seems to be very, very small, as we have 1 upon mc squared in the denominator. Which is rather small, because mc squared for an electron is about 0.5 million electron volts. Okay, so mc squared is roughly 0.5 million electron volts. So that comes in the denominator, and so it looks to be very small. But is it really the case? People have actually observed Rashba splitting, and this is not true. In experiments, one sees larger alpha r values. How is this possible? What one needs to do is actually the following, that is, one must be able to do what is called a k dot b perturbation theory that we have done, which mixes the different bands. Okay, so this is because of the mixing of the bands due to perturbation. So if you are looking at an S band, the S band can actually interact with the P bands above, and this interaction between the S and the P bands can actually reduce the denominator. The denominator, instead of becoming mc squared, becomes actually a gap. So what one has to do is, one has to take the full Hamiltonian, which is h equal to h naught plus h spin orbit, where h naught is equal to minus h cross squared by 2m del squared plus V of r, and then write a pseudo Schrodinger equation for uk of r, that is, use block states psi of k equal to e to the I k dot r uk of r, and obtain the pseudo Schrodinger equation we did this before in the case of effective mass theories, where we did a k dot b perturbation theory, but when we did that k dot b perturbation theory, we did not consider the spin orbit interaction term. So when we do the whole thing, then we get the following Hamiltonian for pseudo Hamiltonian, which is minus h cross squared by 2m del squared plus V of r plus h cross squared by 4 mc squared times grad v cross p dot sigma, where v you have to take the full potential, which is both the spherical potential as well as the asymmetric potential that you have, plus h cross by m k dot p plus h cross squared by 4 m squared c squared grad v cross k dot sigma, this times u of k is equal to E of this. Actually you must also have a band index n, so let me write the band index also. Is equal to E n k minus h cross squared k squared by 2m times u n k of r. Usually the last term, so this term that we have, this term can be neglected. This is rather small, so usually it is neglected, and what we need to do is, if we do this and then do a perturbation calculation which is second order, which mixes the excited p bands with the s bands of our interest. I am not going to show how one can do it. One can always look at the literature and find out for oneself. So what one gets is that the Rashba constant alpha r turns out to be equal to a times T naught times delta SO divided by delta BG. Okay, now let me tell you what these things are actually. So A is the interatomic distance, this comes about because you are trying to hop an electron from one site to the neighboring site, and the hopping is always such that you hop from an orbital to a neighboring orbital. So the hop results in a state where the electron has gone to the neighboring site with a different band index . But same spin. So basically you are saying that un up goes to un prime up, which is the virtual state through this hopping term, which is actually the Hamiltonian, the off diagonal term in the Hamiltonian, and then through a spin orbit interaction term, this goes to un down. Okay, and this one has a amplitude T naught, and T naught contains the field E naught times a matrix element, and the other one, this amplitude is actually delta spin orbit interaction. So that is a spin orbit flips the spin from up to down and also changes the orbital index, because it is actually a spin and orbit interaction. So when you have this, then alpha r is of that form and delta Bg is the band gap between the band of interest and the excited bands. So, what Rashba splitting is capable of doing is that the following: Rashba splitting, Rashba interaction removes spin degeneracy, and the magnitude of the splitting is controlled by E naught. The field. The same thing, in 3D solids, when an inversion center is absent, the resulting spin orbit coupling is called Dresselhaus coupling. So, with this I have completed the spin orbit interactions and the time reversal symmetry as well as the inversion symmetry present in the system and how they actually result in different kinds of splittings of the states. So, in the next lecture what I will do is I will talk a little bit about disordered systems and then I will go over to some optical properties of the semiconductors, and from there we will go to interacting Hamiltonians, where we consider electron-electron interactions which are explicit, because so far we have only been dealing with one electron Hamiltonian, and there we will deal with actually the electron-electron interactions as well. So, I would like to thank you for now, and we will meet again in the next lecture. Thank you very much. Bye.